Okay. In summarizing data data graphically and numerically, we examine data sets such as height and weight with distributions that are bell-shaped. Many variables that measure human physical characteristics are bell-shaped. Imagine for height, for example, there are some people that are very short, some people that are very tall, but the majority are somewhere in the middle. That's why it's not like there are more quote unquote tall people than quote unquote short people. Short people, I guess, is the idea. A lot of things, yeah, like physical characteristics of humans take on this bell-shaped curve or approximately a bell-shaped curve. Might not be perfect. We model these distributions with a mathematical equation that has a bell-shaped curve. These models are called normal curves. They are called normal because the bell-shaped pattern occurs so often. The normal curve looks like this. So let's make observations of normal distributions. Okay, there are many normal curves. Even though all normal curves have the same bell shape, they vary in their center and spread. Okay, let's move down and look at it. Oh, I should clear, okay. Let's see. Because normal curves are mathematical models, we use Greek letters to represent the mean and standard deviation of a normal curve. Normal distributions are symmetric. In symmetric distributions, the mean and the median are equal. Therefore, the mean of a normal distribution divides the distribution in half. We use the Greek letter pronounced mu. I know, like a cat, right? Mu. Whenever I see that, I always think of meow. Meow. Okay, why am I wasting time drawing a cat? You know you love it. I love it. Okay, anyway. To represent the mean. So we'll think of that. If you think of mean, just remember it starts with an M. And what does a cat say? Meow. It also starts with an M. So it almost looks like a backwards Y. You know, a Y looks like that, but it's almost backwards, sort of. Anyway, we use the Greek letter pronounced sigma. 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 To represent the standard deviation. So that would be, and that, I guess that makes sense. Standard deviation starts with the S. Sigma is a Greek letter that starts with the S. Mu for mean. Anyway, so for some reason you know Greek, you know your Greek alphabet. I don't know why, but if you were in a sorority or fraternity, maybe you know these already, but if you don't worry about it. It's fine. To represent the standard deviation of a normal distribution, the standard deviation determines the spread of the distribution about the mean. So for example, the standard deviation of this green curve would be much smaller than of this red curve because the red curve's wider, the average value is further away from the mean or the middle, but the green one's narrower, so it looks like the average value is much closer to the mean than the red one has its average values close to its mean. In fact, the shape of a normal curve is completely determined by specifying its standard deviation. As we will see, if two normal distributions have the same standard deviation, then the shapes of their normal curves will be identical. The following are some observations we can make as we looked at the figure above. Okay, first, the black and the red normal curves have a mean at 10. Let's see, the black and the red. Yeah, because, sorry, there's a lot of stuff going on here. There we go. The black and the red curves, yeah, have the same mean because it looks like the middle value is the same. They're kind of centered around the same place. Okay, however, the red curve is more spread out and thus has a larger standard deviation. Notice that the red normal curve is also shorter. This makes sense because these curves are probability density curves. So the area under each curve has to be 1. So I guess if the area under the red curve has to be the same as the area under the black curve, the red curve is, if it gets wider, that's adding area, so it has to get shorter to compensate, to keep that same area equal to 1. So it's kind of like the red curve has all its area in its width, sort of, but the black curve has all its area in its length, I guess is kind of the idea. But all these probability density curves are all supposed to have an area of 1. That's why that's why I guess they're a little bit sort of, I don't want to say easy. They're not easy to, they're not easy to figure out what they look like, but at least we have that. So, okay, what else can we figure out here? Sorry, let me get this guy. Okay, and we said that. This makes sense. Okay. Also, the black and the green normal curves have the same standard deviation, but different means. Yeah, and that kind of makes sense. Let me scoot up here a little bit. Yeah, the black and the green curves, they have the same width. They pretty much have the same shape, right? So their average value is the same distance from its mean. That's the standard deviation. But the red one, it has the same mean as the black one, but a different standard deviation because it's wider. It doesn't have the same shape as, I guess, the idea. Yeah, okay. And then let's comment about the notation. There's so much notation in math and statistics. That's the hard part to wrap your mind around, I think, to memorize. So we'll use X with a bar over it to represent the mean of data in a sample, but we use mu to represent the mean of a probability curve defined by a mathematical equation. So we're going to keep using this in this class for the most part, but if we ever talk about these curves, we're never going to find the equations of these curves on our own, because like we said, we would need calculus under our belts, but if we talk about them, we use mu for mean. So this is the mean, yeah, like they said, of a sample. That's the mean of one of these curves that we don't know how to find. Yeah, we just know that someone out there knows how to find them. That's what matters, I guess. We use SD or, so capital S, capital D, or S, capital S with a little x subscript to represent the standard deviation of data in a sample. So we're used to that kind of, yeah, one or the other. We use sigma, though, to represent the standard deviation of a probability curve defined by a mathematical equation. So you can kind of think of SD or the S subscript X. These guys compared to this, they're the same thing, but it depends what you're talking about. Am I talking about an actual sample with actual data values that I collected or someone collected? Or am I talking about this theoretical curve that doesn't really have any relation? Well, you probably got it from a sample sort of, but you calculated something that's supposed to approximate the curve, or approximate the area. And then same thing kind of here, you use X bar as the mean if you actually have data either you found or someone else found. But then if you're just talking about this theoretical curve, you're going to use mu.